So let's start the lecture. Can you so if you Toro, if you want to begin recording, you can. Okay. Okay. So this lecture is on visual navigation. Now, wait a minute. We're doing. So this is the problem. You have a robot with a first-person camera, and then I drop it into a novel environment. So initially we did a lot of these experiments were done in Corey Hall, but after a while I thought, okay, you want it to be truly novel, and there'll be ways in which people can cheat because they might have thought of this environment. So all the subsequent experiments we did them by renting Airbnbs. So the rule is you rent an Airbnb, you open the door, you put down your robot, and then you give the robot some task. So my theory is that that way we can claim we have not cheated. I mean, it's a novel environment. Okay. Then the robot walks around, and then it's given some goal. So there are a variety of ways in which to specify goals. So one way to specify a goal is geometric, right? You say go 300 feet north, 400 feet east, right? This is rarely the goals that you actually care about in practice. In practice, what you care about is, oh, I'm looking for the toilet, or I'm looking for a chair, or I'm looking for a knife, or I want to know where is the kitchen. So these are what we call semantic goals. And that's what I regard as what a practical use of navigation systems is, right? Okay, now what is the classical solution to this problem? So the classical solution, which comes from the computer vision community, is called structure for motion. The same solution in the robotics community is called SLAM, but it's exactly the same thing. SLAM is just a renaming of structure for motion. Structure for motion is a term from 1980. SLAM is a term from 2000. So, okay. The idea is that if you have multiple images, then what you do is you reconstruct the 3D environment. Okay. So the 3D environment is reconstructed here. And there are a number of papers that have been written over the years on how to do this 3D reconstruction. And there are still new papers being written. And the latest technology, so the old techniques are all based on finding corresponding points and then doing triangulation. So that's the way you recover the 3D geometry of the environment. The latest techniques involve using learning, where you train on some images, and eventually what you do is you are given a set of images, you recover the cameras, and then you recover the point cloud of the scene. So Duster and Muster are examples of that. Doesn't matter whichever way you do it. The goal here is 3D reconstruction. Once you've done 3D reconstruction, then you solve a different problem, which is called the path planning problem, which is essentially a purely computational geometry exercise. The environment is known, the obstacles are known, and you have to find a connected path between a start and a goal. So this, you can see how this will work for geometric goals. It's not necessarily super smart for semantic goals. What does this approach suggest for semantic goals? Basically, you just keep searching until you find it, right? It seems kind of slightly stupid, right? Okay. The other remark here is, do we really need to? So the classical approach both does too little and does too much. So in what way does it do too much? It does this so in the classical SLAM solution, you first completely reconstruct the environment. Okay, do I need to reconstruct the environment if all I want to do is to go out of the door? No. So it does too much. Okay. It also does too little. Why does it do too little? because it hasn't got this semantic context. It hasn't. So my favorite example for this is you go to some restaurant. This is the first time you've gone to that restaurant. And then you need to go to the restroom. We somehow manage to know which way to go, right? You do not have a map of this restaurant because this is the first time you've been in the restaurant. And yet you sort of have an intuition of, okay, this is more promising. And maybe you'll ask a waiter, but very often you just manage to find the way. Why? Because you have a familiarity with places like restaurants and so on. Okay, the same is true in a home. You go to a friend's home, you don't, what's the slam story? The slam story will say, okay, let's say I want to keeping with this example of I would need to go to the bathroom. The slam solution would say, first I explore my friend's house repeatedly, taking lots and lots of views. Then I built the complete map. Then I'm going to find the way to the bathroom. Do we do that? No. Does this make sense? No. Okay. So geometric 3D reconstruction of the world is insufficient because it doesn't capture the semantic information. It cannot exploit patterns in the layouts of indoor spaces. So all these spaces, we have some sense of where cubicles are, where corridors are. And that's essentially statistical in nature. So what's the technology for capturing that? Machine learning. So you have to find some machine learning way of capturing what are more plausible locations, plausible, more fruitful paths, and so on. Okay. Okay, so let's see. So what has happened is, let me see if I can move this guy out somewhere. Okay. Somewhere around 2016, 2017 is when machine learning techniques became popular in computer vision and robotics. So there was a formulation of this problem, which was either using reinforcement learning or imitation learning. So the idea there is, and it would be goal conditioned, right? So you specify a goal, and the goal could be a semantic goal like chair, or it could be a goal like 300 meters north, 200 meters west. And always the objective is to get to the goal without colliding with obstacles, right? That's our framework. So people started to use machine learning techniques. And there are two obvious ways of doing this. So let's just think that through. So how would you do it with reinforcement learning? I mean, you just keep exploring, right? And then when you hit the goal, you declare success. And then you just do these trials. So in fact, zillions of papers were written on that. And what I disliked about those papers was that they were always solving the problem in the context of one environment, which is, right, you're exploring one environment, and now you can go to different goals, chair, sofa, table, etc. So that doesn't seem so good. Okay, that's one answer. Let's think of, is there a way of converting this to a supervised learning problem or an imitation learning problem? So you find the trajectories. So how can we find the trajectories? We can use the classical techniques. So there is some environment. We have a map of that environment because this is in a simulator. In the simulator, what we did was we scanned in some houses or apartments or restaurants or whatever. So we've scanned in those environments. So we have the 3D map. So in that environment, we can always find optimal paths from any point A to any point B. So these are optimal paths. So now we have essentially the perfect form of supervision. Given a certain target, since I can find the optimal trajectories, I have this oracle, this which knows what's the advice to give you. Go left, go right, whatever. At any location, the oracle can give the agent that advice. So therefore, that's the supervision for the agent. And so what is the agent going to do? The agent gets some visual input. The visual input is shown by this picture. And then, and it has some goal, chair. And then it's a supervised learning problem, because at a particular location, you say, go left or go right or go forward. And you train the network, right? And then how would we generalize? Well, if I have 10 homes, I can train the system on all those 10 homes. And this system will figure out what are more plausible ways to get to the bathroom, for example, in a restaurant. Right? Do you agree? Okay. So people did that. So this is the line. Okay, let's see if there are any subtleties here. Okay, so one approach would be, when you go, you just learn, you just have access to the current image, and you are going to take a step as determined by this policy. So do you see any possible problem with that idea? Huh? So it's static in what sense? The environment is static. So yeah, so there is an issue with like moving obstacles like people. But there is another problem, which is, what if you sometimes there are alternative possibilities, right? And what happens is, you try one possibility and you don't get to the goal. Okay. Next, now you go around and then you are back at the same point. And what will you do? You will do exactly the same thing again, right? You will, so in a maze, you're trying to escape a maze. You're at a certain point and you make you go in a certain way. You always go left at that point, because the visual picture is the same at that point. And you will just keep repeating that mistake repeatedly. So therefore, a purely reactive policy it does not do a clever job of backtracking. So it's always going to screw up in the setting, right? You see that. Okay, so now let's think of what's a possible fix for that. Yeah. Yeah, so now you need memory, right? So you can have memory in different ways. One way of having memory is memory of your past actions. Okay, and presumably the network can figure out, while training, that don't do the same thing twice. The other way of having memory is to have memory of the space. So therefore, either it can be episodic memory, memory of your past actions, or it can be memory of the space. Okay, what does the memory of the space sound like? It's starting to sound like a map. Okay, so the map idea reappears, but this is a smarter version of the map idea, right? Why is it a smarter version? Because you don't go around building the complete map. You just build a map of the areas that you have explored, and you keep a record of it and you use it. But you do not have to start from it's not a blank slate thing. So you can do it in two ways. One is that you can use some LSTM or GRU or transformers or whatever to record your history. The other approach is you build a spatial map. Let's see. And there are papers, like I don't think I'll give you, I mean, you don't need to read references for this. It's pretty intuitive, okay? Okay. Now, this whole game, which, so this in fact happened. There was a series of papers which were all about navigation formulated as a reinforcement learning problem or imitation learning problem but they were in this style of being a reactive system. So the term we use is reactive. Reactive means that it's just using the current information and acting on it. It has no memory, either of your past actions or of the space. And this idea, by the way, goes back ages. People in psychology were studying reinforcement learning for rats in mazes. So the usual setup was, okay, in one place the rat gets some water, in another place it gets some electric shock or whatever, and it's being trained to go in particular directions. And this is like this is called the behaviorist paradigm, and it was very popular in psychology, particularly in American psychology in the 20s and 30s and so on. And then this person comes along whose name is Edward Tolman, who actually was a professor at Berkeley in the psychology department. And there is if you go up on Hearst, you see there is this huge construction going on. That's where the Gateway building is going to be. But the building which was formerly there was called Tolman Hall. And that Tolman Hall is after Professor Tolman, who was like a psychology professor at Berkeley. So Tolman's contribution was he did lots of experiments on rats and so on. You can actually find his lecture. He gave his lecture at Berkeley in 1948, and he said, we have done these experiments on rats in Berkeley and in other places as well. And what his finding was that rats are actually quite smart. So if they go through some roundabout way, but they can find shortcuts. So if you feel that if your theory was that it's all reactive, right, then you would not get this efficiency which you get from building a map. Because once you build a map, then you can find the shortest path. So if the rat has in its brain built a map of the environment, then the rat can find shortcuts. And I'm not going to go into details of this experiment. But Tolman showed quite conclusively that rats must have something like maps in their brain because they couldn't find shortcuts. But even though they never actually traveled on that shortest path, they traveled in some weird way, but they built some kind of a mental representation. And this is quite interesting. This line of work, Tolman was a psychologist. He had not figured out where it was in the brain. But over time, there was a lot of research in this in neuroscience, and the hippocampus was the site where people said the maps are, and then more fine-grained work was done. And anyway, there were people who got the Nobel Prize for those findings on maps in the brain. Okay, so maps exist. Maps are there in the brains of mice and presumably men. Okay, and okay, so I'm not getting through going to go the details of this finding. Okay, so now I'll take you through a couple of papers where so this paper is from it was published in Science Robotics last year, I think. And this paper has a study of comparing these different techniques. Okay, so there are different techniques we can use now for finding paths to a goal, where a goal could be a geometric goal, a goal could be a semantic goal. Okay, so this could be a goal could be, so this is an example of a semantic goal. Go find a plant, right? And then there's some strategy which I'll get into, right? And we did this experiment in that Airbnb style. You rent an Airbnb, put down the robot, then it has to, it does all this stuff, and then it has success when it has found the goal. Okay. Now, these are all examples of various random Airbnbs where the robot is going around looking for various goals. Okay, so now let me. So we had what, 6 homes, three different approaches, 6 goal object categories. I'll show you later a later paper which did this more thoroughly. But from this we got some interesting findings. let's discuss metrics, benchmarks. So when you have a strategy for finding a goal, right? So the goal is you put the robot down and it goes to, it's been told, find a potted plant. And then you want to evaluate how well it does. So I want you to brainstorm a little bit about how to evaluate an approach for navigating to particular objects. You can let the robot run, and then if it manages to find it, you can say success. So it's 1 or 0. If it finds a plant, then you say. Now you're not going to do this in practice, right? You're going to have some timeout. So you'll say, okay, if it finds it in 200 seconds, then it's a success, and if it is not in 200 seconds, then it's a failure. Okay, so that's a reasonable. I mean, that's a good idea. So this is just binary, success or failure. Okay, can you be smarter than this? Yeah.
You can compare the like geodesic shortest distance path, and then if the robot succeeds, you compare how long the distance was compared to the optimal path.
Right. So this is so we can consider normalized path length. Because there might be, you can't just consider the path length because different different targets may have different path lengths. So what you do is you find the optimal path, what is called the geodesic path, and then you find out how much time, how long is the path taken by the robot, and you take the ratio, and that ratio is always going to be greater than or equal to 1, right? So we take the inverse of that, right? So the inverse of that will always be between 0 to 1. So that's a measure of the efficiency. If it always finds the optimal path, then it gets a 1. If it finds a path which is double the length, then its score is 0.5. Okay, we do one practical modification to this idea, which is that I'm not going to wait forever. So I'll have some timeout considered, like 200 seconds or whatever, and that if it doesn't find it in 200 seconds, then we declare it to be a failure. So at that point, the trial is, so what should be the score then? It should be 0. So we call this criterion is called success weighted path length, SPL. So SPL in the navigation community, this is the lingo, SPL. Okay, so SPL, if your robot is doing very well, it'll be 1. If it's always failing to find the target, it is going to be 0, and it's going to be in between. So this is the way we will compare. Now we can compare algorithms. I mean, this is not, I mean, you train it in whichever way you like, but after that, we will compare SPLs. Does that seem reasonable? Okay. Okay, and then we compared 3 different methods. Okay, so let's, so one is the classical approach. So what's a classical approach? You first build a map, then you do, then there's no learning involved. So if I say go to a chair, what it's going to do is it's going to just wander about until it hits a chair, right? So that's the classical approach. Okay, there is end-to-end learning. So what's the end-to-end learning way? Which is essentially, that's kind of obvious. I told you the approach, right? The end-to-end learning is that you are in a simulator. In the simulator, you have apartments of a type similar to what you're going to encounter in the real world. And then you train it in this RL or imitation learning way. And we did this, the parameters are there. That's end-to-end learning. Okay, and then there was this third approach called modular learning. Okay, and modular learning is that we are going to build a map. Okay, so the modules are, one is map building. So we take the idea of building a map from classical robotics. But the map is not you don't do the SLAM thing of going around everywhere to build a map. You just build a partial map based on the area that you encounter. My analogy for this is when I first came to Berkeley, which was 40 years ago, I did not go around everywhere on campus to build up my map, right? I go to certain places and now I have a map of those parts of this campus, and that's it. I always, even now, I have only an incomplete map of this campus, but it is rich in the areas which I go to. I know Soda Hall well, I know Corey Hall well, I know Sutajada Hall well, I know BWW, but I do not know every corner of every pixel of this campus, right? Okay, so these are three approaches, and let me check your like you now we have experimental findings, and those will come. So I'm going to do a little mystery game here. Of these approaches, which do you think does the best, second best, and third? First, second, third. Okay, what's your guess? Let's take a poll. So how many people think that the classical approach is the best, will turn out to be the best? Okay, one vote for that. How many people think that end-to-end learning will turn out to be the best? Okay, two. How many people think that the modular approach will turn out? Okay, so we got the majority vote here. Okay, so yeah, in this case, the majority is right. And now we'll do the so the modular approach turns out to be the best. But what's the second best? So what is the second best approach? Is it end-to-end or is it classical? So now let's take a poll. So now I'm asking you about the second. How many people think classical? How many people think end-to-end? Okay, again, the majority is right. I mean, classical wins. Classical is second best. Okay, and end-to-end is actually a disaster. Okay, in fact, I mean, and I say this because, I mean, everybody is still doing end-to-end, right? So okay, so let's just explain what the specifics are here, but why end-to-end is bad is interesting. Okay, so that's the lesson to be learned here. So this is your canonical way you will build up a end-to-end approach, right? You have some what did it? Okay, so this no, what is this? I can't. I've hidden this guy. I need to move this out. Okay, so this is the end-to-end. Yeah. Okay. Sorry. So you're looking at the image, and then in the modular approach, what you're doing is you're building this map. Okay, map which is partial, and then you have a goal-oriented semantic policy. So you did some learning. What you did learning, the map building, there is no learning. The learning is on what's a promising place to go. That's the part which you do by learning. Okay. And we trained at this time, there were a number of these simulators which had a number of scanned-in environments. So that's what we used. And here are the results. Success rate, okay, in simulation were like this. So basically they're about the same, right? Okay, now the success rate in the real world. Okay. So the end-to-end learning was an absolute disaster. Okay. And note that the classical is quite with classical there isn't so you should always do a sanity check when you hear these papers. So the classical approach, there's no learning, right? So what it gets in simulation and what it gets in the real world should be about the same, and indeed that is true, right? Modular learning somehow it turned out to be even slightly better in the real world. And why that is the case, maybe the distribution of environments in the simulator was harder. It could be. End-to-end learning, why was it so bad in the real world? So think about it and then I'll give you the answer. It turns out to be a disaster mainly because the perception part did not transfer. So the perception part, all it has is the RGB experience in the simulator. And that experience, I mean, while fair amount, it doesn't match the experience of, I mean, there's a sufficient difference between the RGB looks in the simulator versus in the real world. And so the perception part essentially lands up failing. Okay, and this is found many times. I mean, this is not unique to this navigation example. There are other settings in robotics where you'll find the same thing. That the RGB part gets overfitted in the simulator and then it doesn't work so well. And anyway, there are some examples. So these examples show what the SPL was, and these are, so this is a case where a modular did very well, end-to-end was okay, and classical was terrible. And probably the classical did poorly because its exploration strategy doesn't benefit from learning. Okay. Okay, and then we did more experiments, but I've given you the, let's see if I can find some. Oh yeah, so this is this maybe this terminology is worth noting. Semantic exploration versus frontier exploration. So this is something you should know. The semantic exploration is that when I'm looking for, suppose I'm looking for a TV in someone's house, I have a sense of where I'm more likely to find the TV. Right? Frontier exploration means that you just go to whatever is the next unexplored region from your map. So there is no benefit of learning there. So so essentially you get the benefit of that, right? The goal is to go to the bed, and the SPL is 0.90, which is very, very good. With semantic exploration and with frontier exploration, it's not directed by kind of knowledge of where beds are more likely to be found. So end-to-end fails to transfer, and these are all failures of the end-to-end. Yeah. Okay, I think I'll. So there is a domain gap. Basically, the perception. It's a perception where. So my what's the lesson to take from this? I mean, okay, this is just one paper, one set of experiments. The lesson that I take from this is that in robotics, you particularly with respect to perception, particularly with respect to vision, training in a simulator doesn't give you enough data to make a really good vision system. Vision systems, if you train them with real world collection of images and video, there is enough diversity to train really good models. And then you can use them in a simulator. So train in the real for the vision system and then use it in a simulator will work fine. But the other way around doesn't work so well. Whether this is true forever and ever, who knows? But this is certainly the case now. So that's a lesson I would take. Now let me pause here. Let me do a stop share, and I'm going to now go to another talk about a different paper, which is the fancier ways of doing it. Let's close this. Okay, let me just check this out here. Okay. So. Yeah. Okay. So let me check if we are good. Okay. So this is a more recent paper, which let me start with what it is trying to do. This is again the same Airbnb experiment, but just done at a much bigger scale. Okay. So now we use this spot robot, but I mean, we're not using the spot in any sophisticated way. It's got a low-level stack which takes care of moving around and avoiding obstacles. So, but what's going to be done is that it's going to be given various targets like go to the plant, go to the TV, etc., etc. These are all examples. Okay, so this is the setup. So what the goal is, so you can see the observation from the observation and the semantic map, right? You're seeing that. So the map is being built up partially, the and it has a goal, and the goal is indicated. Okay, let me roll this back so it goes a bit slower. So do you see the goal? So the goal here is obviously the kitchen sink. And the goal can be specified in in different possible ways. Let me pause it. We consider three ways of specifying a goal. One way of specifying a goal is you just give a picture. Okay. So then when you find something close enough, then it declares success. Another way of specifying a goal is semantic categories. So a semantic category can be a chair, a desk, a bed, or whatever. Okay. Or the third way to specify a goal could be language. So you have a natural language phrase, and the natural language phrase can be complicated. It can be, the red teddy bear on the green table, right? You can do all of that, right? Okay. Now the strategy that we followed here, I mean, so this is the next. Okay, wait, I don't want to go there. The strategy we followed here was had one. So based on the previous experiment, we already knew that we liked the modular approach. So we were going to use a pre-trained vision system, not a vision system that had been trained end to end. What we were going to do was we were going to build a map because that's a good way to avoid visiting the same place twice. It captures the information in a compact way. But in addition, it wasn't going to be just a classical geometric map. It was going to have a record of the semantic category. So as you go around the world, you say, oh, here there is a refrigerator. So in the map, you make a note, there's a refrigerator. Or here there is a TV, and you make a note of this. So you're going around the environment, you're building the map, but in addition, you're recording uh, these categories, chair, table, etc. And of course, there can be more than one chair. So in which case you need to have a counter running saying chair one, chair two, chair three, etc. Okay, so fairly straightforward. And then where is the other cleverness here? The cleverness has to be and this has to be achieved by training and simulation. What's a place you should go if you think you're looking for a chair? What's a place you should go if you're looking for a kitchen knife? And that you train in simulation, right? But it's a modular approach with some training and simulation for the semantic exploration aspect. The map building is done without, that's like just generic map building. There's no learning involved there. The vision system is a deep neural network, but it has been trained elsewhere on huge amounts of data. Okay. So now let's just play this out. So observation. So this is what the robot sees. There's a goal. It'll keep going, and at the bottom, what you see is what it's recording as the objects it sees, right? So you see all these objects it sees. Then it's declared success. It found the kitchen sink. Now it's been told go to the red cap on the brown leather chair. Okay. But the nice thing is whatever it sees on its way, it keeps recording that. So therefore, it's learning over time. It's becoming over its lifetime as it explores the home. Even while it's doing it for task A, it's going to benefit it on task D. So it's quote lifetime learning, right?
Do you expect the ASPI will become more optimal?
Yeah, so we actually have some experiments that for the same target, after it's gone through the house a little bit, the SPL is better than it would have been in the beginning. So, okay. So this is the goat problem. Okay, so this is the goat problem. So now with full noise. Okay, so I think in this demo, it has to pick up some objects and put it into its. Okay, so the story is cleaning up your house. That's the supposed. Okay, so what was the goal? Multimodal, reach any object specified in any way. Oh, wait, what happened here? Okay, so I thought this should. Okay, wait, something is wrong with the slide. Anyway, oh yeah, I just didn't wait long enough. It could be an image, it could be language, it could be a category. And then it has this lifelong learning aspect, which is how we are here as humans. We never go around first building a map. We just do what we need, but as we go along, we have acquired more and more of the map of the environment. So in my own home, I know it much better than I know in some stranger's home. Okay, goat system architecture. Okay, so this is what we did. We had, okay, sensor pose reading. Okay, so the perception system is basically relying on the power of computer vision community to have built good models for each of these. So there is a segmentation system and depth estimation, geometry. All of this is just off-the-shelf computer vision systems, no end-to-end training here. So this is adequate for building a semantic map, and it is also adequate for recording all these instances, right? Object instance memory. So you have a memory of what I saw at various locations. And this is a sensible thing, right? Because every day when I go, like for example, when I go home, I know, okay, here there is a Starbucks, here there is a bank, here is a grocery store. So our maps are not just pure geometric maps. We also have associations of particular locations and landmarks. So it seems reasonable that you build that in. It's a semantic map. Okay. And then there's a global policy. And okay, so these are the different ways of specifying language goals, image goals, category goals. You feed that as input in some form, and then you it tells you where to go, but you keep building your map. So you may land up making a wrong judgment. You may go left, whereas the target is actually to the right. So you eventually move around, but as your map becomes complete, you will know that this was a unproductive path, because this is happening in the training process as well. Okay, system architecture, I think I did. Perception system. Okay, the building blocks here, let it just roll out. Now, this use depth, I think it could be done without depth, but depth made life easier. Depth was, but it should not really need depth, because the depth information is already there. And okay. Okay, there's a top-down map. I think at this point, I think I've really gone through all the concepts here. Semantic map with associated. Let me just, okay, you've seen all this. The main ideas are build a semantic map, record instances that are seen. And I think I can end here. by just saying we did this and it worked, and it really worked. Okay. And I will end my lecture here.